Welcome back to our deep learning series. Today, we're diving into one of the most crucial activation functions in machine learning, the softmax function. If you've ever wondered how neural networks make multi-class predictions with confidence scores, or how your phone's AI decides between cat, dog, or bird in a photo, this video is for you. By the end of this video, you'll not only understand the math behind softmax, but you'll also implement it from scratch and see it in action. So grab your coffee and let's get started. Let's start with the basics. The softmax activation function is a mathematical function that converts a vector of real numbers into a probability distribution. But what does that actually mean? Imagine you have a neural network that's trying to classify an image. The final layer might output raw scores like 2.1, 0.5, negative 1.3. These numbers don't mean much on their own, right? But softmax transforms these into probabilities like 0.7, 0.25, and 0.05. Now we can say the model is 70% confident it's class A, 25% confident it's class B, and 5% confident it's class C. The beautiful thing about softmax is that these probabilities always sum to 1, and they're all positive, making them perfect for multi-class classification problems. Now let's look at the math. Don't worry, it's actually quite elegant. The softmax function for element I is defined as, let me break us down step by step. For each input zi, we first compute e to the power of zi. This exponential ensures all our values are positive. Then we divide by the sum of exponentials of all inputs. This normalization step ensures our outputs sum to 1. Let's see this in action. If our inputs are 1, 2, 3, we get e to the 1 is 2.72, e to the 2 is 7.39, and e to the 3 is 20.09. The sum is 30.2. So our softmax outputs are 2.72 by 30.2, 7.39 by 30.2, and 20.09 by 30.2 equals 0.09, 0.24, and 0.67. You might be wondering, why use exponentials? Why not just normalize the raw values directly? Great question. The exponential function amplifies differences between values. Look at this. If we have scores 1, 2, 3, simple normalization gives us 0.17, 0.33, and 0.50. Pretty close probabilities. But softmax gives us 0.09, 0.24, and 0.67, much more decisive. This helps the model make confident predictions when there's a clear winner. Think of it as a rich get richer mechanism. Larger values get exponentially larger shares of the probability mass. Let's explore the key properties that make softmax so useful. First, outputs always sum to 1, making them valid probabilities. Second, all outputs are positive regardless of input values. Third, if input A is larger than input B, then softmax of A will be larger than softmax of B. It preserves relative ordering. Finally, softmax has a temperature parameter we can adjust. Higher temperatures make the distribution more uniform. Lower temperatures make it more peaked. Time to get our hands dirty. Let's implement softmax from scratch in Python. I'll show you both a basic version and a numerically stable version. Here's the straightforward implementation. This works, but there's a problem. For large input values, we might get numerical overflow. Let me show you the stable version. By subtracting the maximum value first, we prevent exponential overflow while keeping the mathematical result identical. This is the version you'll find in production code. So where do we actually use softmax in the real world? Everywhere. Image classification, your phone's camera app uses softmax to decide if you're photographing a sunset, a person, or your pet. Natural language processing. ChatGPT and other language models use softmax to pick the next word from thousands of possibilities. Recommendation systems. Netflix uses similar techniques to decide which movies to suggest to you. Even game AI, chess engines use Softmax-like functions to evaluate moves. Before we wrap up, let me share some common mistakes I see students make with Softmax. First, always use the numerically stable version we implemented. Trust me, you'll thank me later when you're dealing with real data. Second, in frameworks like TensorFlow or PyTorch, make sure you're applying Softmax along the correct axis. For batch processing, you usually want axis -1. Third, be aware that Softmax can contribute to vanishing gradients, especially when combined with certain loss functions. Let's quickly compare Softmax with other popular activation functions. Unlike sigmoid, which works for binary classification, Softmax handles multiple classes naturally. Unlike ReLU, which can output any positive value, Softmax outputs are constrained probabilities. And unlike TAN, Softmax outputs are always positive and summed to 1. Use Softmax for multi-class classification, sigmoid for binary problems, and ReLU for hidden layers. Here are my top tips for using Softmax effectively. Always use it in the output layer for multi-class problems, never in hidden layers. Pair it with categorical cross-entropy loss for optimal training. Consider temperature scaling for calibrating confidence, especially important in safety-critical applications. For very large vocabularies, look into techniques like hierarchical softmax or negative sampling. And there you have it. We've covered the Softmax activation function from theory to practice. You now understand the mathematics, can implement it yourself, and know when and how to use it effectively. In our next video, we'll explore how Softmax works with different loss functions and dive into backpropagation through Softmax layers. Don't forget to like this video if it helped you, subscribe for more deep learning content, and hit the bell icon for notifications. Until next time, keep learning and keep coding.